So what we'll do is we'll define our cross product with what I would call as an algebraic definition, and then we'll look at it from a geometric point of view. And then there's a lot of other properties that would follow. So here's a general definition of a cross product. I don't think you'll find a nice definition of the cross product. So because the algebraic calculation involved in finding cross products or numeric symbolic calculation for a cross product is kind of messy. So by definition, you could take a look at these components, but we want to find a more systematic way of doing this. And the way to do this would be using a matrix. So if you've had linear algebra before and you know how to take determinants of matrices, that's exactly what we're going to do. If you haven't, we'll look at it from a determinant point of view. So at this point and in this class, we will only be taking cross products of three-dimensional vectors. Now, when we did dot products, I say you could take dot products of two-dimensional vectors or three-dimensional vectors. And then they went off to say you can even take dot products of 4, 5, 6-dimensional vectors if we need to. But for the cross product, we're really just restricted to three-dimensional vectors. You can imagine going down to 2D, and we'll talk about cases where we might look at it from two-dimensional cross product point of view. But in general, the cross products are for three-dimensional vectors. Cross product for 3D vectors. All right. Now, the actual definition is listed here, but in my statement over here, it's not an ideal thing to memorize this formula. So let's see if we can redefine or use a working definition of a determinant from linear algebra to help us compute the cross product. So what we'll do is when we're ready to take the cross product of two vectors, u and v, it turns out that the order of how we cross them is important. So if we take two vectors, u and v, we will line them up as a second and third rows of a 3x3 matrix. And on the first row, we'll put our I, j, and k. And the way we're going to look at this is a determinant. And the way we're going to compute, one way to compute the determinant is to use what's called a submatrix or a comatrix or something like that. What we're going to do is we're going to run along the top row, and when we do the top row, we're going to pick on each individual element in the top row. We're going to cross out that row and column, and then what you're going to have left is a 2x2 matrix. So the top row, the I is going to go in the top row, or the I is going to be our first value. It's actually a vector, but we'll treat it as if it was a value. And then what we'll do is we'll take the determinant of a smaller matrix. Instead of a 3x3 matrix, we're going to look at a determinant of a 2x2 matrix. And that 2x2 matrix is this 2x2 matrix in this box. And so the determinant of a 2x2 matrix is going down from left to right, the diagonals. That's U2 times V3 and then you subtract the other two components. They're called the wings, V2 times U3. So this actually came from let's see, I'll do it up here. This actually came from the determinant of U2, U3, V2, V3. And so that determinant of a 2 by 2 matrix is the product of the diagonals minus the product of the opposite of the diagonals, which is the wings. Okay? That's the beginning. So when I say expanding, we're expanding along the row, the top row. What we're going to do now is we're going to take a look at the second element in the top row. Now here's the tricky part, and here's the part where people make a lot of mistakes, is that in your expansion, when you go for the first value that you're expanding on, when you go to the next value, the signs will change. So there is going to be a negative sign involved here. And then you'll have J, the J vector. All right, now imagine you're expanding on the first row, you're on that J component, and then you're going to cross out the row and the column that it's involved in, and then what you have left here is another 2 by 2 matrix that you can put together. That 2 by 2 matrix can get put together, and that's U1, U3, V1, V3. And the determinant of that matrix is going to be the same deal that we did. That's the diagonals. That's U1, V3 minus the product of the wings, V1, U3. Okay? Now on to our last expansion. We're on the K. So this went from positive to negative, and then we're going to go back to positive. And then we're looking at the K component. Cross out that first row and that K column. And what you have left is a submatrix, U1, U2, V1, V2, and you want the submatrix that has that information, which is the product of the diagonals, U1, V2 minus V1, U2. Anna? Because that's the rule for taking determinants. If you look at this, it's switched. So I don't know if that's helpful or if this is more helpful. I don't know. If there's something that's confusing you, then cross it out in your notes and just focus on one. I generally, when I do cross products and when I do it in class, I put it into a computer and have it do it for me. But I usually do it this way. This thing in the bottom where it's all positive, that just switches the determinant for me. And so I don't know if that's a good way to remember it. But I would remember it this way. So instead of the original definition, or instead of this thing, which is basically the definition, I would probably want to do the computation like this. Now, there's other people who do determinants slightly differently, and this might be easier for you. I like this way because it reminds me of linear algebra, and if you ever have to take linear algebra, then you should know how to do it this way. But I don't know if this is easier. I think for some people it is. Let's redo this same computation. U is first, right? U cross V. So what people do is they actually extend this a little bit, and then they copy the first two columns, I and J, U1, U2, V1, V2. They copy the two columns. I need more room here. And then what they do is they find the product of these things going down. And then they find the product of these things going up. And notice I have pluses going down and minuses going up. So what you would do is you would collect these terms. I have I times U2 times V3 I U2 V3, the J U3 V1 plus K U1 V2. So those all have a plus in front of them, and then you'll have a negative V1 U2 and the K, negative, this next negative V2 U3 and an I, and then the next negative, the last one, is V3 U1 and a J. And so if you collect all the I's together, factor out the I, we have U2 V3 minus V2 U3. And then you collect the J's. With a plus U3 V1 minus V3 U1. And then you collect the K's together. And that has a U1 V2 minus V1 U2 with a K. So I don't know if this is easier, but this should look pretty much like that formula that we saw on the previous page. It should be exactly the same. So you could do it this way if you want. And the more you do it, the more you'll get used to collecting the I's, J's, and K's a little bit quicker. I just did it kind of slowly because this is initially how people would start. And then once you get used to it, then it should go a little bit quicker. Okay? There's a lot of room for arithmetic mistake here. So you just have to be tedious, meticulous, careful in setting this up. Okay? So that's the algebraic way of computing cross product. Any questions? All right, let's take a look at some geometry behind the cross product. The cross product, much like the dot product, has a geometric definition that involves a sine, or in this case, a cosine. The cosine rule is a little bit trickier, or the sine rule is a little bit trickier because, oh, by the way, this cross product is sometimes called a vector product because why? Because your result is going to be a vector. The dot product is sometimes referred to as a scalar product because your result is a scalar. So here, your result is a vector. So when you start trying to combine the geometry behind this, there could be a lot of geometry in 3D that we're going to try to visualize. But in terms of sines and cosines, you have to be a little bit careful in looking at it from a scalar point of view. And so the first thing that you see here in the geometric definition is you're taking the magnitude of the cross product. I don't know why I only have single bars here and double bars on the others. Should be consistent, huh? Let's put another bar there. But you know, you're flexible enough now, right? If you see a single bar, double bar, it still means magnitude. And it could work for vectors or scalars, because for scalars, the magnitude is just the absolute value. So the first thing you notice in the cross product is that the cross product of two things is the magnitude of v, magnitude of u, times the sine of the angle between them, but you're not looking at the cross product itself, you're actually looking at the magnitude of the cross product. So that's the first geometry of this. And more importantly, this is where the more important geometry comes up, I think. It turns out that the cross product itself, if we not take a look at the magnitude, but just the cross product itself, the vector result that you get is going to be the length of that vector times n, where n, what have we been using n for? Normal vector. So what this is telling us is that the cross product is actually going to be a vector, another vector, that's going to be perpendicular to those two vectors. I wonder if that's mentioned here. Nope, I should mention it, and then we'll take a look at these other geometric properties. So what I want to mention is that the cross product is a vector that is perpendicular to the two vectors being crossed. Being cross. Now, if you take two pencils and hold it tail to tail in front of you, imagine a perpendicular vector to those two pencils that you're holding in front of you. What do you notice? Try it. Nobody's holding up two pencils. If you hold up two vectors, and then you want to make a cross product, so you take another pencil, and what are you going to notice? Use your fingers if you have to. If you have two vectors, what's your cross product going to look like? Here's my pencil. What should I do with my pencil? How's my cross product going to look like?
If you're using your right hand, your thumb.
What? Perpendicular to both, right? I need to have a vector. This vector has to be perpendicular to both. Now, the tricky part is that there's two possibilities for this. So the tricky part is that your cross product will either look like one of these two, but you can only have one answer. So if you imagine this cross product of these two vectors, I have two possible answers. I have an answer where it's going one way and an answer going exactly the opposite way. Okay? So that's not good in math. We want something that's going to give us one unique solution in general. That's what we want. And so to figure out which normal vector you're talking about, you have this idea of what's called the right-hand rule. So the right-hand rule tells us that when you cross u and v, where u is the first vector and v is the second vector, what you want to do is you take your right hand. Let's see if I could draw a hand. And then you wrap your fingers. What? You tripping?
No, it's on the
So, hold up your two fingers again. Let's say your index finger is the first vector you're crossing and your middle finger is the second vector you're crossing. Hold up your two fingers with your left hand. Take your right hand. You're going to wrap your four fingers around to your index finger first, and then wrap it around to your middle finger after that. You feeling me here? Take your right hand, you're going to wrap it between your index finger, you're going to wrap it around with your index finger first. Okay, your right hand is the finger that's wrapping around your two vectors, and whichever way your thumb is pointing is going to be the direction of your normal, of your cross product. So if you wrap around from u to v, then your normal vector will be going in this direction. Now imagine if you switch the cross product and you've got your middle finger first and then your index finger second. You want to wrap your middle finger first, so I need to take my right hand and wrap it around this way. And now my cross product will give me a normal vector that's going the opposite way. That's your right-hand rule. Okay? All right, I should probably stop drawing. Yeah, never mind. All right, so that's how you figure out which way your graph is going. Your normal vector, your cross product vector is going. So the idea, that's one idea behind which normal you're going. So if I have the same drawing here, U and V, and for this one, instead I say I wanted V cross U, then I would wrap my fingers around going this way, and then that would give me a normal vector that's going down. Okay? Now, the right-hand rule and the order of the vectors really just describes the direction of the normal, but the magnitude of that should still be the same. So these two, U cross V and V cross U, should be exactly the same except for the direction that it's going, which means I should be able to write those two in an equation, right? And what is going to be our first important property for the cross product? U cross V is equal to negative of V cross U. And the word for that is anti-commutative. It's not commutative. You switch to order. Commutative means if you switch to order, you get the same answer. So if you switch to order and you're going to be off by a negative sign, it's called anti-commutative. Okay? What? Cross product. Let's see what this program thinks I wrote. Cross-frodoped. I'll have to deny this. Can I change this? It says cross product here. You guys are learning to read my writing, right? Well, hopefully by the end of the semester you can at least hopefully be able to read at least 50% of my work. All right, so that's the perpendicular part of the definition, of the geometric definition. There's other special types of geometry that's involved with a cross product, and let's take a look at some other of those properties. And let's try to justify it too. Cross product of two vectors that are scalar multiples of each other is 0. Scalar multiples of each other. What's that mean if two vectors are scalar multiples of each other? Going in the same direction. Or it actually can mean they're going in the exact opposite directions as well. So they're either going in the same direction. That's supposed to be the same direction. Or exact opposite direction. In either case, well, in the first case, what's your angle? And in the second case, what's your angle? So 180 degrees or 0. And, well, what's the sine of 0? And what's the cosine? What's the sine of 180 degrees? So sine of 0 is 0, sine of pi is 0, which means, according to the geometric definition, you got, let's call this U1, or U and V. U cross V is equal to, what was it? Something with a, oh wait, we got the absolute value here. And it's equal to the magnitude of U, magnitude of V, and sine of the angle between them. And if your angle is either 0 or pi, then this whole right-hand side will be 0, which means the magnitude of this is going to be 0. Which means the cross product itself would be equal to 0. Now, when I take out the magnitude and put just a plain old regular cross product, I'd have to say that this last equation that I wrote isn't quite correct. And there's one minor thing I want to do here to make it complete. What is it? This last one is not quite correct.
Do we need a direction?
Close. So, not quite a direction. If you're 0, then you don't have a direction. So, the thing is that the cross product is supposed to be a vector product, which means your result is a vector. So, having a 0 vector is different from having a 0 scalar. A 0 vector is 0, 0, 0. depending on what dimension you're in, but it's zeros as components of a vector. A zero scalar is just the number 0. So those two are significantly different in terms of the things that we're dealing with. So we want to be careful with that. And in linear algebra, there's a zero matrix, which is even different from a zero vector and a zero scalar. So we have to respect that. The next geometric property is saying that the magnitude of the cross product is the area of the parallelogram created by the two vectors. Now these are three-dimensional vectors that we have. And so say we have a couple of vectors in 3D. You can actually look at them from a two-dimensional point of view. If you look at them from a two-dimensional point of view, imagine that they make up a parallelogram. And amazingly enough, that length or that magnitude of the cross product is exactly the area of the parallelogram. Now, how's that true, or why is that true? Well, if you really want to know, look at the parallelogram on a two-dimensional plane. If you just imagine looking at it from the top. And let's find the area of the parallelogram. Area is base times height, right? And if it's a parallelogram, it's been skewed a little bit, you still have to find the base times the height. So imagine trying to find the height of this. So the base, let's call this U and V. And so in terms of lengths, we just call them the magnitudes of U and V. So to find that height, the base is U. To find that height, you if you imagine including an angle here and just focusing on this right triangle with a hypotenuse of V and an opposite side that you're trying to look for. Let's call it, I don't want to call it, I guess it doesn't matter if I call it X. Let's call it OP for opposite. That opposite side will be your height. Oh, why don't we just call it H? That opposite side will be your height. And how would you find that opposite side? Well, H is going to be, the sine of theta is opposite over hypotenuse, right? So if you work that around, write it down if you want to, but if you're working around in your head, you'll see that your height is equal to the hypotenuse times the sine of the angle between them. And so the area of this whole parallelogram is base times height. And the height was, or the base was magnitude of U, and then the height was magnitude of V times the sine of theta. That's exactly the geometric definition of the magnitude of the cross product. That's by definition, magnitude of the cross product is equal to that. So that's another way to show that the area of the parallelogram is, in fact, the magnitude of the cross product. Okay? Any questions? All right. There should be a handful of algebraic properties as well. Now here's a visual. I wonder what this one does. Yeah. It's not a big deal. All right, some other algebraic properties for the cross product that might be useful. Well, the first one is the anti-commutativity that we've already talked about. The second one talks about a scalar being distributed, and the third one is the distributive property. So the scalar being distributed looks a lot, actually the 2 and 3 look a lot like the dot product properties. And the first one, aside from the negative sign, looks just like the commutative versus anti-commutative properties. So it all kind of mirrors the dot product properties. So some of these properties might come in handy when we're working and deriving things, when you're trying to find out what happens when you cross things. So I think the dot product properties, in terms of algebra and proving things, they're a little bit more important. But there's some value in these properties as well. We need to manipulate some of the cross product work that we do. All right. What else? Is there anything else on this page? Oh. When you need an equation of a line, what do you need? Back in algebra? A point and a slope, right? If I give you 2 points, could you still find the equation of the plane or of a line? Yeah. So you would do some connecting things, and then you would find the slope, and then you'll use the point and the slope business to come up with the equation of your line. Well, it turns out that for a plane, if you have 3 points, you have a well-defined plane with 3 points. And so here's another approach to finding an equation of a plane, this time when you're given 3 points. Oh, I don't have an actual example. Guess we'll have to come up with 3 points. So if you have 3 points, you have a pretty well-defined plane. Just like if you have 2 points, you have a well-defined line. And so it would be good to be able to find the equation of this plane. So let's make up 3 points. What's our first point going to be? What? Just make it up. 3D. We're in 3 dimensions. 1, 1, 1. That's nice and boring. Next. 2, 4, 5. And then another one. Throw a negative in there somewhere. Negative 3, 6, 7. The only thing we want to be careful about is that they don't all fall on the same line, because if they all fall on the same line, then our plane, that we don't really have a well-defined plane. So our plane crashes. So we've just been talking about the cross product. How do you think you can incorporate a cross product with these 3 points? You have first of all, you have 3 points. You don't have 2 vectors. Wait. 2 vectors. You need 2 vectors to make a cross product. Let's just make 2 vectors. So let's make 2 vectors out of this. What vector should we use? I don't see any vectors there. Yeah, let's define the vector. So give me an example of a vector, and then we'll try to find it, given these 3 points. Do you understand what I'm asking?
Negative 2, 7, 8.
And how did you get that?
By subtracting the top point, -367, from point 111.
So which way is the arrow going, the way you said it? Not that it matters, but...
From 111 towards -367.
All right, let's call that vector u. So u is equal to, let's do it carefully, because the order is going to be important when you're finding these vectors. For this, in general, for these problems, it doesn't matter what the order is, but since we called it u from one point to the other, let's actually compute it correctly. So I think I have a -3 minus 1, 6 minus 1, and 7 minus 1. So what's my u vector equal to? 5 and 6. All right. Now, let's have another vector v. And it turns out, let me tell you now, it turns out that it doesn't matter which way v goes as long as it involves this other point, 2, 4, 5. So we have like four choices. You can either make it connect with this first point or the second point, and then you can make it connect in any order. And I'm saying it doesn't matter, and we'll take a look at why it doesn't matter. Let's do this. Which way do we want the arrow? That way. Again, it doesn't matter, because if the arrow was going the other way, then we could just imagine moving it around. So our v vector is going to be 2 minus 1, 4 minus 1, and 5 minus 1. So we have two vectors now, and these two vectors are on the plane. To find an equation of a plane, I should have started off with this. To find an equation of a plane, you want a point and a normal. You want two things. You want a point and a normal. You have 3 points to choose from. Let's not worry about the point. Let's try to find a normal. To find a normal, we found two vectors that are on the plane. So if I cross those two vectors that are on the plane, I'm going to get a vector that's perpendicular to those two vectors, which means I should be able to get a vector that's perpendicular to the plane. So depending on how you cross them, also, it doesn't really matter, because it doesn't matter if your normal is going up or down. It's still going to give us the same result. So let's use purple for a normal. N is going to be, and it doesn't matter which way we do it, we'll say u and v. U cross v. So I, j, k. The first vector u, minus 4, 5, 6. A second vector v, 1, 3, 4. So now let's figure out the I component. And the I component, it's going to be 5 times 4. That's 20 minus 3 times 6, 18. 20 minus 18 is 2. In my j component, which is negative, I cross out the j, and I have a negative 4 times positive 4. That's negative 16 minus 1 times 6, 6. Negative 16 minus 6, negative 22. And then in my k component, I have a negative 4 times 3, that's negative 12, minus 1 times 5, minus 5. Negative 12 minus 5, negative 17. So let's put minus negative, just so we're kind of clear. See how easy it is to make a mistake? Meticulous. Have to be meticulous. So let me rewrite this in terms of just a vector without the I, J, and K. So I can write this as 2, positive 22, and negative 17. So that's my vector, normal vector. I drew two normal vectors on my plane. Which one is it? The one going up or the one going down? Right hand rule. I didn't label V, but U is that first vector. This is V. So which one is it? The one going down. So that's a normal vector that we just found. All right. Now I have a normal vector, and I have 3 points to choose from. I'll just choose any of those 3 points. Let's choose 1, 1, 1. So we have a point and a normal. Now, it was only yesterday that I showed you the equation of a plane. Do you guys remember? Should I just tell you? Remember, it's n dotted with the variables x, y, z is equal to the same normal vector dotted with a particular point on the plane. So I have 2, 22, negative 17 is my normal. So 2x plus 22y minus 17z. That's the dot product between the normal vector and the x, y, z. And then I need to dot this vector with 1, 1, 1. So if I dot it with 1, 1, 1, I'll just say 2 times 1 plus 22 times 1 minus 17 times 1. And this is equal to 7. Okay? Now I said there's 3 points here, and I just randomly chose one. What if we chose another one? We better get 7. Are we going to get 7? Let's choose negative 3, 6, and 7. So this is going to be negative 6, 22, and 6 is, it's what? 132, 7 and 17. 49, 119, and let's do this subtraction. Equals 7. It worked out. Right? It better have, because we're claiming that any point that we use should give us the same plane, and this is our unique way of getting a plane. So if you try it with 2, 4, 5, you should get the same thing.
So we're saying that the plane is 7?
No, you're saying that the plane is 2x plus 22y minus 17z is equal to 7. That whole thing is your plane. In fact, let's just write it down and box it. 2x plus 22y minus 17z is equal to 7. And how you got that 7 doesn't matter whether you use the first, second, or third points. You should always get 7 for that. Okay. Any questions? So we're getting a good jump on this studying the plane business. All right, let's see if there's another application for the cross product. Parallelopiped. Do you guys know what a parallelopiped is?
Sounds like a parallelogram that's been sweeped.
So parallelogram that's been swept. A parallelepiped is a parallelogram from two vectors that's been swept along a third vector. It gives us the volume. So it doesn't go up and down, you know, like how we swept the cylinders that we were messing around with some time ago. So in 2 dimensions you have a parallelogram. If you take that parallelogram and sweep it to the third vector, along the third vector, then you would have that volume. So that's just the base of it. But if you take that base, let's do it like this. Up there, and then connect. You have a 3-dimensional parallelogram, so to speak. Parallelogram is really a 2-dimensional thing, but a 3-dimensional parallelogram is called a parallelepiped. So it turns out that the volume of this involves the cross product of some sort. And we can derive it with a base times width times height. If you cross u and v, right, you would get the volume of the parallelepiped. You'd also get this vector that's perpendicular to u and v. And then to get the volume, you would take the dot product of that third vector, w. So the volume is going to be given by, I guess the order here doesn't matter because you're looking for a volume which is a positive quantity. So at the end, you'll eventually take the absolute value, so it doesn't matter. And it turns out that you can switch the order of this, of u and v and w, and you put them in any order you want, then you're still going to get the volume if you take the absolute value. Okay? All right, I didn't do any examples with numbers. Should we try to do one real quick in 4 minutes?
Now, when we say that the magnitude of the cross product is equal to the area of the parallelogram,
Mm-hmm.
so if we find that just simple numbers, that the area of the parallelogram is 4 square units,
Mm-hmm.
does that mean that the magnitude is then 4 on the resultant vector?
That would just be the area of the parallelogram. But here you're not taking the magnitude of this.
I'm not talking about the
Yeah.
volume. I'm just talking about
Yeah.
the cross product.
Yeah. So the cross product is going to be, when you take the magnitude, it'll be positive, and that's the actual length of that normal vector is the area of the parallelogram. Yeah. In terms of units, you're looking at the length of that. The magnitude is a length, which is 1-dimensional, but the area is 2-dimensional. So it's just one of those things where numerically it's the same numeric value, but in terms of units and physics and stuff like that, it doesn't quite flow that way. All right. Let's see if I have an example here. I don't have numbers, I just have the drawing. Okay. Let me just make up 3 points, or not 3 points, but 3 vectors. And if I want to find the volume of the parallelepiped, what I need to do is I need to cross 2 of them first, and then dot it with a third one. So let's see. Let's cross these 2. Wait, did I already do this? Are these the same numbers? Let's make it the same numbers. Now they're the same numbers? So what was the cross product again? Okay. What? Oh, no, we didn't cross it like that. All right. Never mind. I was trying to do a all right, so can somebody do a cross product real quick? Let me see if you're faster than Wolfram. Well, I have to type it in. U cross V. Hurry, did you guys get it? I won. 1 negative 10, 9. Good job, guys. All right, so we got the cross product is equal to this. Now we're going to dot it with this. So W dotted with U cross V is equal to 2 times 1, 4 times negative 10. This is a plus, not a comma. Plus 5 times 9. And that is equal to whatever. What? 40? 5? Two and 1. What? 7? Okay. All right. Now, we did this in 2 steps, right? We did the cross product, which was difficult. Well, not for me because I use Wolfram Alpha. But if you were to do it using the matrix, you'd set it up with a matrix. But before we let that go, this answer 1, negative 10, 9, when you guys initially would have done the cross product, you probably would have seen that as I times 1 and then minus 10j plus 9k, right? And then when you dot it with this, look at the difference between what you got in the cross product and this next step of the dot product. You see that? So what I'm trying to say here is that to get the volume of the parallelepiped, when you do W dot U cross V, and again in any order, what you could have done is you could have just put the U vector here and the V vector here, and then you would have ijk on top. Instead of putting ijk on top, the I gets replaced with a 2, the j gets replaced with a 4, and the k gets replaced with a 5. That's exactly the W vector on top. Do you see that? So you can write your matrix like this. Instead of ijk on top, just have the first vector and then the other two vectors, and then calculate and it'll work out. And the order doesn't matter either, so you can switch any order. All right. So tomorrow, quiz, and then we'll do some lines and planes.